DBSCAN, which stands for Density-Based Spatial Clustering of Applications with Noise, is a popular clustering algorithm. Unlike k-means, it doesn't require specifying the number of clusters beforehand. Instead, it finds clusters based on the density of data points, allowing it to discover clusters of arbitrary shapes and identify noise points effectively. Think of finding groups of stars forming constellations in the night sky. DBSCAN relies on two key parameters, epsilon and minPts. Epsilon, or epsilon, defines the radius of the neighborhood around a data point. Any point within this distance is considered a neighbor. minPts is the minimum number of neighbors, including the point itself, required within the epsilon radius for that point to be considered a core point. Core points are the hearts of clusters. Based on epsilon and minPts, DBSCAN categorizes each point into one of three types. A core point is in a dense area, having at least minPts neighbors within its epsilon radius. A border point is on the edge of a cluster. It's reachable from a core point but doesn't have enough neighbors itself to be core. A noise point is an outlier, not belonging to any cluster. It's neither core nor reachable from a core point. Let's look at a concrete example to understand these point types better. Here, with minPts set to 4, points like A and the other red points are core points because they have at least 4 neighbors within their epsilon radius. Points B and C are border points. They don't have enough neighbors to be core points, but they're reachable from core points. Point N is a noise point. It's neither a core point nor reachable from any core point. Now let's see how the DBSCAN algorithm uses these concepts to form clusters. The DBSCAN algorithm follows these steps. First, we define the epsilon and minPts parameters. Then, we iterate through each point in the dataset. If the point hasn't been visited yet, we find all its neighbors within the epsilon distance. If it has fewer than minPts neighbors, it's initially marked as noise. It might become a border point later if a nearby core point claims it. If it has minPts or more neighbors, it's a core point. We start a new cluster with this point. We then expand the cluster by finding all points density reachable from this core point. This involves exploring the neighbors, and the neighbors of neighbors, and so on. Any point found during this expansion that isn't already part of another cluster is added to the current cluster. Core points stay core, while others might become border points. We continue this process until all points have been visited. Finally, the clusters are formed, and any points still marked as -1 are confirmed as noise. Let's visualize DBSCAN. We start with our data points and defined epsilon and minPts. The algorithm iterates through points, identifies core points, and expands clusters until all points are visited. Noise points are left unclustered. DBSCAN offers several advantages. It can find non-spherical clusters, effectively handle noise points, and doesn't require you to pre-specify the number of clusters. K. However, DBSCAN is sensitive to the choice of epsilon and minPts. It can struggle with clusters of vastly different densities and may perform poorly on high-dimensional data due to the curse of dimensionality. Use DBSCAN when you anticipate non-spherical clusters. Need to handle noise. Don't know the number of clusters beforehand. Or are working with spatial data. Avoid DBSCAN if your clusters have very different densities. The data is extremely high-dimensional without pre-processing. Or if k-means assumptions, like spherical clusters, fit your data well and speed is critical. Thanks to its ability to find arbitrary shapes and handle noise, DBSCAN is used in various fields. Its explicit noise identification makes it excellent for anomaly detection, finding unusual patterns in financial transactions, network traffic, or sensor readings. In geography and urban planning, DBSCAN helps identify dense residential areas, points of interest clusters on maps, or seismic activity zones. It can group users with similar tastes or behaviors, even if those groups form complex patterns, improving personalized recommendations for movies, products, or content. In bioinformatics, DBSCAN can help identify clusters of gene expression patterns or group proteins with similar structures or functions. In conclusion, DBSCAN is a powerful density-based clustering algorithm, particularly useful when dealing with non-spherical clusters, noise, and when the number of clusters isn't known in advance. Choose it wisely based on your data's characteristics. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.